We've talked about the Gibbs energy being a special indicator for spontaneity for processes that occur at constant temperature and pressure. And while this is the case, sometimes we need to know what that Gibbs energy is, or what its change in Gibbs energy is, at different temperatures. So we'll be interested to know sort of how the Gibbs energy is affected by the temperature at which a process takes place. Now, to get a handle on that, I'll note that we had a while ago an indication that the variation of the Gibbs energy with temperature at constant pressure was equal to minus S, which is clearly less than 0. So what this tells us essentially is that the Gibbs energy as a function of temperature decreases because the entropy is a positive quantity. So this decreases with increasing T. But that doesn't give us an idea of how quantitative that is. So what we want to do is see how we might learn something more quantitative about the variation of G as a function of temperature. Now, I'll also say that this applies to changes in the Gibbs free energy, just as it applies to the function itself. So that means we can sort of expand on this relationship up here to say that the partial derivative of the change in Gibbs energy with respect to temperature, evaluated at constant pressure, would be equal to the negative change in the entropy. Now, this will be important because most of the time we're going to be wanting to evaluate for a process in which Gibbs energy has changed. We want to evaluate how that change in Gibbs energy changes when we look at a different temperature. Now, I'll also note parenthetically out here that delta G is going to be effectively equal to H minus, that's a minus, T delta S. And if I solve for the delta S here, it's going to be equal to 1 over T times delta H minus delta G. So in other words, this thing out here that I've written as minus delta S is in fact equal to 1 over T times delta G minus delta H. Now this is going to come in handy in just a moment because we're going to need to use it to simplify an expression that we're going to get. The expression that we're going to get, though, comes from taking the following derivative. I'm going to take this derivative and subject it to conditions of constant temperature, constant pressure. But the thing I'm going to take the derivative of is the Gibbs energy divided by the temperature, or the change in Gibbs energy divided by the temperature. Now, when I take this derivative, if I take the derivative of the Gibbs energy part, I'll still have the 1 over temperature out here, but the derivative I'll have will be the derivative of the change in Gibbs energy with respect to temperature at constant pressure. I will also get a derivative if I take the derivative of the 1 over T part. So then I will continue to have a factor of the Gibbs energy. The derivative of 1 over T is minus 1 over T squared. And then I'll have a partial of T with respect to T at constant pressure. But of course this is just 1. All right, so it seems like a crazy thing to do, but bear with me because this will hopefully make sense very shortly. All right, now what I'm going to do is to say that, okay, if I clean this up a little bit, it'll be equal to 1 over T outside of some barrier times this derivative, d delta G with respect to temperature at constant pressure, minus, I'll have another factor of 1 over T here, times delta G. Okay, and this was just 1. All right, now this quantity here is given up here. It's equal to minus delta S, but I could also write minus delta S this way. So in fact, I can write this as 1 over T outside, and this derivative is equal to this expression. So I'll have 1 over T times delta G minus delta H, and then minus 1 over T delta G. So I think you can see where this is going. These two terms are going to cancel one another. So I'll end up in the end with an expression that looks like this. So the derivative of delta G over T, so I'll write it like this, with respect to temperature at constant pressure is equal to this. And this expression that we've just developed is what is known as the Gibbs-Helmholtz equation. And this equation is what tells us how the Gibbs energy is going to change with temperature, or changes in the Gibbs energy change with temperature. And they go basically as the enthalpy over the temperature squared. Now, there is a similar relationship that one can find for the Helmholtz energy, and I'll just report that here without deriving it, but it would follow a very similar derivation, where I would have d of delta A over temperature with respect to temperature. Instead of constant pressure, it's at constant volume, and it would be equal not to the enthalpy but to the internal energy over temperature squared. So this is a companion form of the Gibbs-Helmholtz energy, or you could call it an alternative form of the Gibbs-Helmholtz equation that is also valid for these things. All right, there is an interesting video that you may want to watch in the lesson that will tell you how to physically integrate this Gibbs-Helmholtz equation to get other equations that might give you a more direct path to evaluating the temperature changes that a change in Gibbs energy would incur.